So we've seen, I'm going to leave this up, we've seen this sort of generalization of the small set expansion theorem from the hypercube to product spaces. Unfortunately, products are really dense, which does often make them sort of hard to use in certain applications. There are nice applications of this on the p-biased cube, but for a long time after this point, other than like a few sort of one-shot examples like the Weizmann that we talked about before that have been extremely useful, we were sort of stuck. It wasn't really clear what to do beyond this. So sort of what's the next direction? The fact that I'm teaching this in a high-dimensional expander course, it means you probably know what the next direction is going to be. So I want to make the following observation, that products have a natural interpretation as partite simplicial complexes. This is maybe something we've sort of referenced previously throughout the class, but we haven't really talked about it in any detail. So if I have a product space, this is like, you know, the Cartesian product of some sets 1 through n on the hypercube. These are each 0, 1. But you could be more, you know, you could be n to the k or something like that. You could be more general. And then these corresponding distributions. Well, to view this as a complex is not all that difficult. I can just sort of draw out each of the each of these is going to be like a part of my partite complex. Right, so I think maybe let's just draw a picture. So we have like, this is like the set omega 1. This is like the set omega 2. Here's omega 3. Here's omega, let's just do 4, like n equals 4. So what is this object? Well, these are all just like tuples where I take one thing from each of these parts. Right, so maybe there's an edge where I take, you know, sort of these particular vertices from each part, and this is like a 4 set. So we can define a complex, right, which is like the corresponding complex x4 is just exactly like this Cartesian product. I'm taking all possible combinations of one thing from each part. So this is like the complete 4-partite simplicial complex. And I'm taking a little bit of liberty because I'm not telling you about these distributions pi I, but again, you know, I'm just producting the distributions. Let's just pretend they're uniform for now. It doesn't really make that much of a difference. Okay. So a product can be viewed as this partite simplicial complex. And then maybe the second interesting observation, it's going to motivate sort of what we do further here, is that products are actually, I mean, maybe you sort of already see this from this diagram, products are perfect high-dimensional expanders. So products are 0, maybe I'll say like partite, one-sided, 0 local spectral expanders. So on a partite object, this is as good as you can hope to be, right? Things that are partites, the negative eigenvalues are really bad. They're like -1, at least at the top dimensional lengths. But everything else is like the best possible thing you can hope for. In the partite setting, this is like the perfect model for an HDX. So why is this true? Somebody tell me why this is true? Why are products 0 local spectral expanders? Yeah, okay. I mean, what's the structure of a link? The structure of a link is like a complete partite graph, right? So, you know, links are complete multipartite graphs. I mean, I'm not saying anything. This is like a trivial observation, but we should make it. And okay, I have cheated here slightly. Right? I've ignored this product, these distributions pi 1 through pi n, but okay, they're like productly weighted multipartite graphs, and you can still show that these are 0 spectral expanders. So this sort of implies that, you know, the links are 0 spectral, all one-sided expanders. great. So that's one really nice connection. We've proved this theory for products that sort of generalizes the theory of the hypercube. And now I'm saying products are a really special case of high-dimensional expanders, of partite high-dimensional expanders. And what's more, the connection goes much, much deeper than this. If I look at sort of many types of analysis tools that have been introduced on products, like the noise operator. So you have a question?
Yeah, sorry, it might be 10 seconds late, but what is a partite simplicial complex?
Oh, good, thank you. A partite simplicial complex is just like, this is just a complex where each vertex has a color. So in this case, like each vertex comes from some part here. This is like color 1, this is color 2, this is color 3, this is color 4. They're corresponding to the coordinates of the product. And xk always has like one of each color.
So when you say that products are partite simplicial complexes, you're really talking about like one level?
Yeah, I mean downward close this object and you get the simplicial complex.
But then when you downwards close it, those won't be in the product anymore.
Sure, I mean it's a way you can.
I'm trying to understand.
Okay, this is a very good point, actually, and it's a point I wasn't planning to make, but I should. One very common way to analyze products is to look at conditional distributions. It's to look if I like condition on the values. If I look at this product and I like condition on the first values being 1 and 3, and I do some sort of conditional analysis. This is like a very classical thing to do in a product. This is a link, right? So this simplicial structure actually just corresponds to like conditional analysis in the product. So it is sort of okay. While we don't formally think of this product as this having these downward levels, it actually does. These are the conditional distributions of the product. So implicitly, the rest of the complex structure actually is there when you analyze the product. That's a really good question. Okay. And good. So links are sort of like conditional distributions. That's a good point. The point that I wanted to say is that if you look at the noise operator, which we defined up here, first of all, notice that there's a very natural generalization of this to a partite simplicial complex. The only difference, so I'm still going to go through every part. So remember, in my partite complex, I have one vertex. In my k-face, I have sort of one value from each part. And I'm going to do the same thing where I go through each of my coordinates, I go through each of my parts, and I remove each one with probability 1 minus rho. And now instead of like independently resampling the things I removed, I'm just going to look at sort of the collection of things I removed, and I'm going to resample them all together, conditional on the rest of the values. Is that a statement that makes sense? So let's say that we have this string is x, and I have like values, I don't know, a, b, c, d, and e, and I go through sort of this noise process where I like remove A and I keep B and I remove C. Now I'm going to look. I'm going to look at the link of sort of B, D, E here, and I'm going to resample the values of coordinates 1 and 3, conditioned on the fact that maybe it's better to see on this graph. Right? I'm going to like remove this guy and this guy. So now I'm sort of just like on this edge here, and then I'm going to resample the values here, just conditioned on the 4 edge containing these 2 vertices. So this is just like resampling something from the link of what's remaining. Right, that's all I'm doing. And what does this sound like? When I take the lower walk, this is exactly what I'm doing. Right? When I take the lower walk on a complex, right, I start at this k set. And then I just remove elements one by one until I get down to an I set. And then I conditionally resample the rest of the values, right? This is exactly what is happening here. So maybe to phrase things in the language that we've talked about in this class, the noise operator is actually exactly a convex combination of these higher order random walks. And we can actually, let's just write it out. So the noise operator is equal to the sum from I equals 0 to n of, this is like a binomial distribution, so in other words, this is like a convex combination of these lower walks. So what am I doing? I'm saying in the, what happens to the noise operator? I remove, okay, here I'm doing it sort of bit by bit, but this is, I remove some subset of coordinates, right? And that subset of coordinates is drawn from like a binomial distribution with probability rho. So what I'm doing here is really just taking, if I remove I things, or if I end up with only I things left, this is just like taking the k to I to k walk. Right? So this noise operator is exactly equivalent to this convex combination of walks that we've studied in this class. And why is this the same? Like if my complex is a product, when I do this conditional resampling, the things that I'm resampling have no dependence on what I'm conditioning on, because that's the definition of a product. Everything's independent, right? So the sort of natural generalization to a general partite complex is I'm sampling conditionally, but when I restrict back to the case of this like complete multipartite setting or a product, I get exactly the standard noise operator back. So all of this sort of machinery on products, the study of like conditional distributions and the noise operator, all of these are strictly generalized by higher order random walks on partite simplicial complexes and on high dimensional expanders. Okay, any questions about that? Okay, so this raises a natural question. We've said products are perfect high dimensional expanders. We've said all this theory that we've developed in this course is all a generalization of exactly the things I've been talking about for the rest of this lecture. Expansion, the behavior of higher order random walks, and the noise operator. Okay, so there's an obvious question. Does this type of behavior generalize to partite high dimensional expanders? We can rewrite this theorem above, by what I've said. We can already sort of rewrite this theorem above as like X sort of is like a zero local spectral, partite zero local spectral expander. I think that's true. This is only products, right? Maybe I should be careful, but X is a product, i.e. like the complete multipartite complex, or something like that, I should say.
The matroid walks are also zero local.
But they're not. Isn't a partite matroid like a fully partite matroid? Is it?
Not partite, is that it?
Yeah, the ones that aren't products aren't partite, I think. Okay, I should be a little bit more careful. I think that's true, but maybe it's not. So we'll say X is complete multipartite. That's at least true.
Oh, maybe you're right.
I'm not 100% sure, so I won't make the claim. It's also not in my notes. It's a riffing on. So can we generalize this from complete multipartite to like a bounded degree high dimensional expander, something really far away in many ways? Okay. So I want to talk about sort of why you would expect to be able to do this and why not briefly. So we've seen that sort of in a spectral sense, high dimensional expanders, with this, when I rebuilt this sort of Fourier basis, they act similarly to, in that case it was the complete complex, but by similar arguments you can kind of show that the complete multipartite and high dimensional expanders in the spectral way do act very similarly. But we also saw that like products in the cube acted the same way spectrally, and yet they had sort of quantitatively different behavior. So that doesn't necessarily mean this is going to generalize. The other reason you might not expect this to work is that there are a lot of behaviors on bounded degree simplicial complexes that are very different, very quantitatively different from products. For instance, if you look at like the mixing time of this operator on a product versus a bounded degree complex, it'll be extremely different. Because on a product, you just have to resample every coordinate once, and then there's no dependencies, so you're like immediately mixed. But on a bounded degree complex, this is like a bounded degree graph, so it takes a much longer time to mix. And things like mixing turn out to be extremely related to small set expansion. There are these things called log Sobolev inequalities that are all related. I don't want to go too much into it, but these are all related, and it's not unreasonable to sort of think these don't have the same behavior. Why would we be able to sort of generalize this type of theorem? Okay, given that I'm standing here talking, it's not that surprising that the answer is indeed, we can replace this assumption, with X being a partite gamma local spectral expander, where for safety, I'm going to say that gamma is like 2 to the negative poly n, but you can probably do better. So like exponentially good in the dimension local spectral expansion will imply, let me declutter this a little bit. Will imply this theorem with no modifications. Like we were discussing in the break, this is interesting because in many ways, products and high-dimensional expanders are extremely different. Bounded degree high-dimensional expanders have enormous dependencies between them. If I like restrict on the value in the first coordinate in a product, it has no effect on the rest of the coordinates. If I restrict on the value of the first coordinate on a high-dimensional expander, there's only a constant amount of things that are left. Right? I'm looking in a link. It looks very, very sparse. So it's sort of surprising that you can get this behavior to generalize. And now I sort of want to tell you the key reason that it does work. Why can we actually? I've said all these reasons why maybe like you would expect it not to be true. Let me tell you actually why it is true. And then the last hour we'll move to hypercontractivity and get our hands a little bit dirtier. Okay, so maybe I'll title this section, R partite HDX product-like. Okay, I think for me personally, the easiest way to think of this, so previously I said you can take a product and you can embed it very naturally as a partite simplicial complex, and all of these different machineries that we've built match up. Now I want to say the other way is also sort of true. Not that a high-dimensional expander becomes a product, but I can take any partite simplicial complex, and I can think about it as a collection of n joint random variables. Right? So I can take any like n partite simplicial complex, and I can think about it as a joint distribution over n random variables, where these variables are just the value that the complex is taking on each part. Right? When I draw a top-level face, I'm getting one value for each of these things. This is just like drawing from a joint distribution on n variables. So what is a product in this case? Well, now we're sort of back in the traditional setting. A product just means like all the xi are independent. Right? All these, if I'm the complete multipartite complex, or I'm coming from a product, all of these are completely independent. It doesn't matter at all how I condition. It's always going to be the same distribution, no matter what I say x1 or x2 or any subset of these things are. Right? It's completely independent. And the point that I just made before is, if you look at it like a bounded degree, or really anything that's not a product, this is going to introduce dependencies to the random variables. Right? And in particular, in a bounded degree complex, and something where the links are of constant size, like I said, these variables are like as far from being independent as possible. Right? I condition on a value of x1. Suddenly there's only a constant, there's like 10 options left or something. This is a huge amount of dependence. And it might be that sort of the marginal probability of some element before over here was like 1 over the domain size or something like that. And now I condition. I like condition on x1 being a, and suddenly it's like a tenth. It jumps from like basically nothing to some huge probability. So there are these massive dependencies in an n-partite simplicial complex, and this is why you might initially expect that proving this type of theorem would be hard. So now let me say sort of the key observation for, yeah.
The same argument can go like against why those constructions can be expanded, right? So it's like, how can it expand like in the general,
Yeah.
expansion when constantly like that is?
Yeah, this is true. Yeah, I mean, okay, the key thing is going to end up being like exactly that you can get this sort of expansion behavior. But yeah, you're getting ahead of me. Yeah. Okay, so one way, what I want to look at is sort of how to quantify the correlation between variables here. in a complex. And what I'm going to do, I'm going to look at like the marginals of this. I'm going to look over a subset. I'm going to take sort of disjoint subsets S and T of like parts of this, disjoint subsets of variables in here. And I'm going to look at the marginal distribution on S and the marginal distribution on T. And I want to talk about sort of the correlation between these two sets of variables. If we're thinking about things in complex language, this is just like I restrict to looking at the things that are coming from color S, or I restrict to looking at the things that are coming from color T. You can always move between these two languages. I just find this one a little bit easier in this context. OK, the way that we're going to quantify sort of the correlation between these variables is by an averaging operator. It sort of takes functions, something very similar to like the down and up operators that we discussed that moved up and down between levels of the complex. But now I'm going to move sort of between colors of the complex. I'm going to move between its parts, which makes more sense in the partite case, or makes equivalent sense. So I'm going to look at what I'm going to call the two-set averaging operator. EST. And this is going to basically be the walk between XS and XT. EST is going to map sort of functions. Let me make sure I don't sort of flip the indices around. This is going to map functions on XT to functions on XS. And it's going to do it by averaging, just like we did on the up and down operators. So I think this is probably easiest to see. Let's walk over here. It's easiest just to see by defining it. So EST F at X. So here F, remember, is a function over XT. So F is some like function on color T to R. And the value here, so X is now, maybe I should write XS. This is just something over coordinates S, over colors S. This is going to be the expectation over my full joint random variable, over my complex, of the value of F evaluated on coordinates T, conditioned on the fact that at coordinates S, I'm fixed to XS. So I'm sort of just looking within the link of XS at coordinates T is another way to think about it. So I'm conditioning on ZS is equal to XS. So there are lots of ways to think about this. Right? This is like sort of the bipartite operator that's capturing the correlations between S and T. It's the random walk between the color parts. It's like you can look at the adjacency matrix, the bipartite adjacency matrix of this. These are all sort of ways of capturing correlation between these parts of the complex. And now the key observation, or maybe I should say like on a product, EST is going to correspond to like a complete bipartite graph. Because there's no, again, there's no dependence at all on this. If I have my two parts, and I fix some value of x over here, all possible values over here are still available because there's no dependence. On a partite simplicial complex, this, on a bounded degree complex, this is like a bounded degree bipartite graph. Right? I'm going to erase like most of these things. And the key observation, which is actually due to Yotam and Aritz in a paper on agreement testing sort of a while back, is that while this is now like a bounded degree graph, if you're on a high-dimensional expander, then it's actually an excellent bipartite expander. That EST, the like second largest singular value of this, is at most something like O of S times T times the local spectral parameter. So what does this say? Maybe I should say like here. This says that, yes, while it's true that at a pointwise level, I can't decorrelate xi and xj. Right? Xi and xj have a huge amount of dependencies, but somehow when I'm looking at things spectrally, they are independent. When I look at things on average, being a good expander is basically exactly telling me that I can decorrelate the behavior of my function on coordinate set S and coordinate set T. Maybe let me sort of finish this part by being slightly more concrete by what I mean by decorrelating, just so we can really see what this is letting us do and sort of why this is going to be really helpful for proving this type of theorem. So we're frequently going to be analyzing, I mean, this is even true in the second moment, but we're frequently going to sort of be analyzing things like f as a function on coordinate sets S, g is a function on coordinate sets T, and xs and xt are drawn like jointly over my whole distribution. The point is that drawing something jointly, I can also write this as like first I sample xs, and then I sample xt conditional on xs. Right? So what does this mean? This means I can exactly rewrite this as like, okay, first let me rewrite it like this. Fs, xs, and now I sample xt conditional, or I'll write it like this, where I'm sampling xt conditionally, right? I'm saying where I'm realizing I should have used different variables, but where I've sort of fixed, let me call this zt so that it matches, where I'm sort of fixing zs to be xs. This is just this definition that I wrote down here, right? So this is unfortunate because I've run out of board space, but I'll fit it in here. No, that won't work. Okay. Sorry. So this means that this is equivalent to just plugging in the definition. This is f of xs est g of xs. And the point here is that because this is an excellent bipartite expander, this is very close, right, up to like difference in the spectral gap, to just the independent product of the expectation of xs and the expectation of g on xt. So like on a product, this is just a strictly true statement, right? These, because xs and xt are independent, you can completely decorrelate them. What this theorem is allowing us to say is that if we're analyzing expectations, which we'll see in a moment is exactly the type of behavior we need to analyze to understand small set expansion, then this is true approximately. It's true up to some O of gamma error, and we can sort of hope to just go through the machinery used on products and replace everything with O of gamma where we need to. And this will indeed be true. And this is sort of roughly how this theorem is proved. Okay. Any questions on this before we go into hypercontractivity? Okay, great. So I think we can get through the Bonomi lemma. We'll go there. Do we want to take? Yeah. Do people want a break? Yeah. Okay. It's a good time for a break also, because the next thing we're going to go into is like pretty separate. I mean, it will prove this, but it needs separate setup. So yeah. Okay. Let's take like a 10-minute break. Whatever it is. Okay.
See if I can find the talk.
Uh-oh. The mic was covered. I hope it's not a... Yes. Good. Good. I know how to use electronics. Okay, sorry. Maybe I should say, from before, I should have credited the theorems that I was talking about. The version of the theorem that I gave for high-dimensional expanders is actually due to Siki and Tom Gurr and Noam Lifshitz. A very similar version for unordered complexes in the two-sided regime was due to myself, Matali Kaufman, and Shachar Levitt. And you can check out those papers if you want to see the exact proof, or maybe at some point I'll go over a simplified version later on. But sorry for forgetting to credit there. So now we're going to make a little bit of a shift. We're going to talk about a very powerful tool set in Boolean function analysis that allows us to prove these types of small set expansion theorems. And I think we will actually be able to get through enough stuff that we'll basically see how to prove the original small set expansion theorem. So this tool is called hypercontractivity. I'll maybe mention why in a bit. Let's briefly remember our standard Fourier analysis on the cube. So we can always split f into its Fourier basis, which are just these multilinear polynomials, right? We sum over all s of the character chi s, which is just the product across xi for everything in the set S. Very standard. F is like a function to the reals, I should say. We'll define fi to be the ith level of the Fourier decomposition. This is the contribution from all of the coordinate sets that are of size. I shouldn't use I to be the same thing here. So let's make this j. J. And then f less than or equal to I will, again, be the contributions from everything at level I and below. And remember, the reason to care about these things is that Arit mentioned before. First of all, these things, which are the characters, these were the eigenvectors of Cayley graphs on our object, on plus minus 1 to the n. And moreover, the eigenvalues only depended on the size of S. So all of these fi together span like a single eigenspace of the hypercube of these graphs. So typically, we'll often work with also when we were doing these HDX decompositions, we were talking about fi. It's the same thing, right? Same idea here. OK, so sort of what we've seen is that the Fourier theory that we've seen so far, like that we talked about at the beginning of the class, that these are the eigenspaces, that they're approximately orthogonal, Parseval's theorem that you can move between the Fourier basis and the standard basis under a 2 norm. These are all sort of inherently statements about the second norm of f. They're like they're all sort of looking at this type of inner product structure. And what we'll see soon is that, and we also saw that sort of on the hypercube and the p-bias cube and products, that like this was sort of all roughly the same. It had similar behavior up to sort of the 2 norm. And what we're going to see is that to sort of understand this small set expansion behavior beyond sort of the second eigenvalue and things like this, it's going to be really important to have a way to control higher norms of the function f. Maybe I'll just put as a reminder here that our goal from the very beginning of this lecture was to control the amount of Fourier weight on level I. Right, our goal was to sort of understand this quantity, because when we wrote out expansion of a set S, non-expansion, this was equal to the sum of lambda I times this quantity. So this is really what we should be focused on, figuring out how to bound. And maybe I'll sort of just leak ahead of time for like the small set expansion theorem. What you need to prove is that small sets have very little projection onto sort of low Fourier weight when I is small. OK, so let's move back over to hypercontractivity. OK, so I already said this is sort of a way to understand how to control higher moments of f. We're going to be focusing on a very special case of hypercontractivity called the Bonami lemma, which I'm apparently going to misspell. And the Bonami lemma is basically a way of saying that the low degree Fourier parts, the low level parts of a function, are smooth, act nicely in some sense that we'll quantify here. Then what is true? The function that looks just like on the projection to the first I levels of the Fourier decompositions, like all the Fourier weights up to level I, as we said. The 4 norm of this function is not too much bigger than its 2 norm. And I'll explain roughly sort of why this is at all a reasonable thing to say. Because I think the first time I looked at this, I had no intuition for why this is like something reasonable to look at. OK, so this is the Bonami lemma. And OK, in the case of the hypercube, I'll just mention an equivalent way to say this. F less than or equal to I, what is this? These are just like multilinear polynomials of degree at most I. Right? So another way to say this statement is that degree I, or like low, maybe I'll say low degree. Low degree multilinear polynomials are smooth. Okay, why am I using this word smooth? What does that have anything to do with this quantity? Well, intuitively, this sort of, imagine I have like a spiky function that has a lot of its mass sort of concentrated in one place or one value or something like this. When I take higher norms of that function, this sort of spike gets blown way out of proportion. When I take higher norms, it amplifies sort of this spikiness, and I would get some behavior that I would see the 4 norm being much, much larger than the 2 norm, because I'm raising sort of this large part to the 4th power instead of to the 2nd power. We'll see an explicit example soon, but that's the idea. Spiky functions get blown up by higher norms. So what this says is that the weight is sort of nicely or smoothly distributed. If you're familiar with working with like probability and random variables, another way to think about this 4 norm versus 2 norm characterization is like, it's like a niceness condition on a random variable, right? You can have a random variable which has like a nice finite second moment or variance, but has like infinite 4th moment, has like some crazy behavior when you look at the power of the variable to the 4th. This is some niceness condition saying like, the functions we're looking at are reasonable. They don't have this crazy behavior, at least up to low degree. They sort of act smooth and nicely everywhere. And indeed, we won't see it in this lecture, but you can very quickly from this, in sort of the random variable view, derive things like concentration, like types of Chernoff bounds or anti-concentration, that are these like very nice behavior of these variables. Okay, so typically that's sort of the two ways to look at it, is this like spiky versus smooth trade-off or like a niceness condition on variables. We're going to look at it sort of this like spiky versus smooth functions. And let me now like quantify this a little bit just by looking at a set that has density alpha. And this should also tell you, I mean, it's going to bring this connection to what we're doing over here. So let's say I have a set S of density alpha. So in other words, the expectation of 1S is equal to alpha. So let's just compute what these quantities are. Right, so first of all, I'll say that for now I'm going to ignore so this less than or equal to I. I'm just looking at what the 4 norm of this function is. So the 4 norm of 1S is the expectation of 1S to the 4th to the 1/4. So what is this in terms of alpha? Alpha to the 1/4. Right, so 1S is an indicator. It's a Boolean function. It's 1 or 0. Right, so it doesn't matter what power I raise a Boolean function to. It's always going to be the same Boolean function. Right, so this is expectation of 1S to the 1/4 is equal to alpha to the 1/4. Okay, an easy calculation. We can do the same thing for the 2 norm, right? 1S2, that's a lot of lines, I'm realizing. Let's do this. I wasn't trying to make the notation as bad as possible, but maybe I will next time. Okay, so now, just by definition, that's this, right? And again, we apply the same trick, right? 1S squared is 1S. So this is alpha to the 1/2. Now think of alpha as something small, right? Like 1% or something like that. Alpha to 1/4 is way, way, way bigger than alpha to the 1/2, right? I mean, we can just look at this ratio. We can look at like the 4 norm divided by the 2 norm. This is equal to 1 over alpha to the 1/4, which is really large when alpha is something small. So what is this saying? Like, why am I looking at this? Notice that this like completely fails this quantity, right? The 4 norm of this function is being blown up hugely. It's being blown up sort of proportional to its density. And this should tell you that sort of sparse functions, they can't have very much projection when I is low, right? When I is small, it's exactly saying like this behavior doesn't happen. If I think of I as being like 1 or 2, then this is the claim that like, you know, the 4 norm of this function is at most like 3 times its 2 norm. which is very different than the behavior I'm getting here. So it can't be the case, like if most of this function 1s, if most of its projection was onto f1 and f2, it would violate this statement, right? You get a contradiction between these two things. So intuitively, this tells you sparse functions cannot have much projection onto these low Fourier spaces, onto low eigenspaces, which is exactly what we were trying to do over here. Now let me give you a concrete argument that actually formalizes this. Any questions before I give the argument? But that's sort of the intuition. Sparse functions are spiky, and therefore they can't satisfy this smoothness of low degree polynomials. Yeah.
So you use the banana lemma and the contrapositive way, right? So.
Yeah, essentially. Right. This thing does not look like what banana lemma says, and therefore it can't be this thing. Good. So let's now prove what's called a level I inequality, which is exactly what we were trying to do before. I have to remember what the exact value is here. So this is like a quantification of what I just said. For any, f is any Boolean function of density alpha. So f is a Boolean function of density alpha. And I'm saying that its projection onto, say, like, constant levels, or even like log 1 over alpha levels or something like that of the Fourier weight is very small, right, if alpha is small. OK, so the proof of this is a very nice trick. It's very short. So let's just start with this quantity we're trying to bound. OK, I'll tell you that the first step is going to be some inequality where we try to like decorrelate these things in a way that we can apply Bonami. Does anyone have an idea of what to do here? We want to get to some way to apply this. Yeah. So okay, I mean you could also write this as like fi. I mean it's equal because they're orthogonal. But I'm not going to do this. I want to sort of actually decorrelate these sides. So okay, maybe this first step like isn't so intuitive, but I think it'll be sort of clearer as soon as we do it. So what I'm going to do is I'm going to apply Holder's inequality. And I'm going to decorrelate this inner product to be just about a norm of f and the norm of fi. We are actually going to do what you said like 2 steps later. So Holder says that this is at most fi 4 norm times f 4/3. So Holder, maybe I should remind people what Holder is. Holder says that fg is less than or equal to, this is like a generalization of Cauchy-Schwarz, q as long as 1 over p plus 1 over q is equal to 1. So when p and q are 2, this is Cauchy-Schwarz. This is like a more general way of decorrelating variables, and it's extraordinarily useful. And when you're analyzing higher moments, like half the time you're going to be applying this inequality. So if you ever want to work on this sort of thing, definitely go check out. Also using like tightness of various cases, it's really extremely like core in analysis. Okay, anyway, that's sort of an aside. So we've done this. Okay, now what do we do? We have some forward norm. We want to talk about the 2 norm. Yeah, we should use the Bonami lemma. Thank you. Use Bonami. Okay, so the 4 norm we can bound by, I'm cheating a little bit here because I'm using like equals I instead of less than or equals to I. It doesn't matter. This is true for like an arbitrary degree I, up to degree I polynomial, which includes degree I, exactly degree I polynomials. Okay, so I apply Bonami. this gets me what? Root 3 to the I, fi2, f 4/3. OK, now I want to shift this back over to this side. Now we're going to use what you said. Right? This is because of the orthogonality of f and fi, this is equal to root 3 to the I f fi to the 1/2, just replacing fi here with f because all the other terms are 0 by orthogonality. And then maybe let me at the same time do, well, no, we'll do that in the next step. F 4/3, so this is using orthogonality. OK, so of course I'm eventually going to shift this over here, but let's do one more step. What is this 4/3 norm of f? Remember, f is Boolean. So we're going to use the same trick that we used over here. Right? We're going to say this is like expectation of f to the 4/3 to the 3/4, but this is Boolean. So this is just expectation of f to the 3/4. And this is what we've defined as, this expectation of f is alpha. Right? So this is alpha to the 3/4. So maybe together, this term gets replaced with alpha to the 3/4. So we'll write this plus Booleanity. OK, now let's divide this out back here. Right, so this gets me fi is less than or equal to, or maybe I should say fi to the 1/2 dividing out is root 3 to the I alpha to the 3/4, square both sides. This is alpha to the 3/2. OK, and how do I get to the final step? Sorry? Yeah, good. The final step is that alpha, which equals expectation of f, well, f is Boolean. This is also equal to the expectation of f squared, which is ff. So I just divide out by ff on both sides. OK, so this gives us this level I inequality. And how do you prove the small side expansion theorem given the level I inequality? I'm going to leave it to you to go through as an exercise, but I'll tell you the pieces, which I said before. I have this expression for expansion up here. You need to also compute what these lambda I values are. For the noisy cube, it turns out that these are equal to rho to the I. So it's an exercise to go through and see, basically I'm going to, for the levels where rho to the I is large, I'm going to bound things by Bonomi. They're going to be proportional to the 3 to the size of I times the density. And then once I get past I being like roughly log 1 over alpha or something like that, now all the eigenvalues are also proportional to alpha. So at the end, I'm going to get something proportional to alpha to the O of 1, which is the small side expansion theorem.
So the key thing is that the eigenvalues will decay.
Yeah, it's very important that the eigenvalues here are decaying exponentially fast.
Because for the hypercube, it would be like a line.
Yeah, exactly. And this is the answer to the question that you asked before.
Okay.
This just won't be true on the hypercube for this reason. OK. Any questions on this? OK, maybe one question is like, why is this called hypercontractivity? What does that have anything to do with what I've written here? So let me, as like a brief aside before we prove the Bonomi lemma, which I think is going to be, unfortunately for me, fortunately for you guys, the last thing that we'll do today. Let me tell you why it's called hypercontractivity. So this is actually in reference to a different version, a different equivalent version of the theorem that, happily enough for us, has to do with the noise operator, which we've talked about at length. So this is called the 2 to 4, this pen is dying, hypercontractivity theorem. And it states just the following, that for any rho, this was like our noisy hypercube rho value, less than or equal to 1 over root 3, this root 3 and the Bonomi lemma root 3 are not an accident. Okay, these are going to be the same thing. We have that the fourth norm of T rho applied to F, I should say, for any F on the hypercube, that the 4 norm of T rho F is at most the 2 norm of F. Okay, what is the statement saying? It's saying that T rho is like a really, really good smoothing operator. Not only, so what would it mean for T rho to be contractive normally? This would say just that T rho F2 is less than or equal to F2. This is just like having a second so the largest eigenvalue is like 1. Right? This is contracting 2 norm. If I'm contracting like P norms or something like this, I'm looking at the same norm on both sides. This is like a much harder, starting in a higher norm, it's much harder to smooth down to a lower norm. This is where the hyper and hypercontractivity is. It's contracting 4 norm to 2 norm instead of 4 norm to 4 norm. And you can prove maybe not getting like exactly, actually no, you can get 1 over root 3. There's like I've told you that the eigenvalues of T rho F, the eigenvalues of T rho are like rho to the I. And you notice that I've picked rho to be 1 over root 3 here. That seems to exactly cancel this term in the Bonomi lemma above. So there's a way to prove this theorem by just dividing this out into its Fi components and being slightly clever with how I apply the Bonomi lemma to get to this sort of inequality. So you can move between these two as like equivalent formulations. But this is sort of why it's called hypercontractivity. An equivalent way to think about this is about the contractivity, or sort of how much the noise operator smooths out functions on the cube. OK, unless there are any questions about that, let's actually prove the Bonomi lemma. Go over here. Lost the eraser. Okay, so the high-level idea is that we're going to do an induction on the number of variables. Okay, I'll mention sort of the key reason that you can do this. First of all, instead of thinking of like the low degree parts of a function, it's equivalent to just say, let's assume we have, G is a degree I multilinear polynomial. So I'm just gonna, it'll be easier to just move to the language of polynomials for the proof. And the point is going to be that I want to divide, I want to induct on the number of variables here. So I should say on n variables. Right, so G is some function of like x1 through xn, where every term is like x1, x3, x4, x7, etc. And I want to induct on degree. So let's write the statement. We want to show that expectation of g to the fourth is at most 9 to the I expectation of g squared squared. So if I take the fourth power on both sides, this gives me back the Bonomi lemma. It'll be much easier to not work within, inside a fourth power or something like that. There's no reason to do that. Okay, and we'd like to assume this for all functions assume for all g on n minus 1 variables, does anyone have an idea how to sort of divide g up so that we could try to apply an inductive version on one fewer variable? So g is this like, sum of multilinear terms like this. So let's say like I wanted to remove in some way the variable xn. Yeah, we're just going to divide g into the monomials that have xn and the monomials that don't have xn, right? So we can write g as xn g prime plus g prime prime, where this is all the monomials in g that contain xn, and now I'm pulling out xn from that product, and this is all the monomials in g that didn't contain xn at all. So this stays exactly the same. And what's the point? Right, the point is that by definition, g prime prime is a function on n minus 1 variables. It doesn't contain xn, right? So this is a polynomial on n minus 1 variables. And this isn't quite, right? The product of these isn't, but g prime, this is, not only is this a polynomial on n minus 1 variables, because I pulled out xn, it's also of one lower degree, right? Because it doesn't, every term had xn, and I've removed it. So this is like a degree, and this is, of course, of a degree at most I. So this guy is also a polynomial on n minus 1 variables of degree at most I minus 1, because I've removed one variable from every monomial. OK, that's sort of the setup for the induction. Maybe I'll sort of leave that here. And now let's actually do the induction based on this information. So first we should do the base case, right? So what's the base case here?
N0.
N0. I'm going to do this until I hit constant functions. Right? The zero-dimensional hypercube is just like the empty set. Right? So the base case is n equals 0, and this is just this is the constant part of g. So let's say it's like c, some constant c. Then what do we have? What's the expectation of a constant to the fourth? Yeah, it's still the constant. It's had no dependence. There's a sort of a stupid way to write it. This is c to the fourth. Expectation of c squared. I mean, it's a constant, right? It's still c to. I mean, now it's c squared, which is c to the fourth. Right. So these guys are equal, which is what the Bonami lemma says for 0. Right. Bonami says. I mean, there's no root 3 to the 0 is 1. So this is what we want. Okay, this is good. This is the base case. Let's do the inductive step. This is slightly more interesting, but one of the cool things about this is that really, once we sort of realized this, the proof will more or less write itself up to like 1 or 2 tricks using Booleanity or using balance of plus minus 1. So let's just write out like what expectation of g squared is and what expectation of g to the fourth is, and we'll try to compare them. Right. So first of all, let's start with the easier of the two. OK, I mean, clearly I'm just going to expand this in terms of the decomposition that we had. So I'll do that part for you guys. So expectation of xn g prime plus g prime prime squared. This is equal to expectation of xn squared g prime squared plus 2 of the cross terms plus just this final term squared.
Doesn't the cross term die?
Okay, good. So the next thing I was going to ask is, can we simplify this? And okay, I didn't clock who it was, but somebody says, doesn't the cross term die? And the answer is yes, the cross term does die. Why? Because xn is independent of g prime and g prime prime, right? So this is like, I mean, if we really want to write it out, this is like expectation of xn times, doesn't really matter, expectation of something. This is a plus minus 1 uniformly random bit. So this is 0. So this cross term dies. This is nothing. And then what's xn squared?
1.
Xn squared is 1. Great. Okay, so this was really this was great, right? This simplifies all the way down to expectation of g prime squared plus expectation of g prime prime squared. So you think the hard part must be the 4 norm. No, not really. There's going to be like one additional step. It's going to be basically the same thing. But let's maybe like do it on this board, just so we make sure we have enough space and like constantly lose the eraser. I'm not used to these boards that slide. Okay, great. So now we're going to analyze. I need a new. I think the good marker is also above my eyesight level. Much better. Okay, now we're going to analyze expectation of g to the 4th. I won't torture you into telling me what all the terms are. We already saw that xn squareds become 1, and things that are of odd parity of xn will be killed, right? So I'll spare you literally foiling out this 4th power, and I'm going to kill all the cross terms that are xn and xn cubed, and we'll set all the xn squareds to 1 and xn to the 4th, so 1. So just writing this out, we'll write this step at least. And then applying all these same tricks that we had up here, this is just going to be expectation g prime to the 4th. That's the term where I've written xn to the 4th is 1. The odd cross terms all die because of having odd dependence on xn. So we also need the squared term. And this will have like a binomial coefficient, right? So this will appear 6 times. This will be 6 expectation g prime squared g prime prime squared. And then we'll have the g prime prime to the 4th term. Okay, so does anyone have thoughts for the next, yeah? Yeah, on the middle term? Good. Okay. So we need to separate. We don't know how to deal with the product of g prime and g prime prime. We've got to do like something similar to what we did up here when we divided things out. This time we aren't going to need Holder. We're just going to need Cauchy-Schwarz. Good. So Cauchy-Schwarz says what? G prime to the 4th plus 6 expectation g prime to the 4th to the 1/2 expectation g prime prime to the 4th to the 1/2, just using Cauchy-Schwarz, g prime prime to the 4th. This is using Cauchy-Schwarz. Great. What's the next step? Induction. These are all, we can now finally use these assumptions that we had on g prime and g prime prime because we've completely separated them out into their own terms. And I've set this up with the right coefficients, such that this should exactly work out unless I screwed something up. So let's see what that happens. So G prime is the degree I minus 1 guy, although I think actually here that won't matter. But so this will be 9 to the I minus 1 expectation G prime squared, right? Applying, yeah, I mean, I'll just do it for all of them. Plus 6. Let's do this inside like a square root. This will be, again, here will be 9 to the I minus 1 expectation G prime squared, 9 to the I expectation G prime prime. Let's actually make this readable. G prime prime squared. And then this term will be 9 to the I. This is just the degree I component still. Times expectation G prime prime squared. Okay, I'm going to pull out 9 to the I, and we'll see what this looks like. So this is equal to, here I'm just going to lose a factor. Expectation G prime squared plus whatever this gets us. So this is like
You're putting out an
9 to the I over 9, which is 3. So this will end up being 6 over 2, and I pull out the 9 to the I. Sorry, 6 over 3, which is 2, and I pull out the 9 to the I. So this should be 2.
you're putting out 9 to the I minus 1.
No, I'm pulling out 9 to the I.
So you should have 1 over 3 or something, no?
Here? Yeah,
Okay.
it's loose. This isn't an inequality. Because the inner term is going to become the second moment. So actually, you can do like slightly tighter things if you have like some assumption on structure and don't lose this term. But for the basic lemma, we just lose a factor here. Okay, and then this just exactly pulls out. The reason at this point, right, is we wouldn't know what to do if we ended up with like G prime prime and G prime being unbalanced. Like now it's not clear how to handle this in the next step of the proof. So we sort of just lose a little bit on one of the, we balance it to the worst of the two.
Less than we
Yeah. Good. Yeah, it's not true otherwise. Okay, and this is just expectation G prime squared plus expectation G prime prime squared. Okay, now I actually mean it when I write equals here. Okay, now why are we done? If I draw 2 there? Good, because this is what we said the 2 norm was. Okay, so this is just expectation 9 to the I expectation of G squared, and we've proven the vote on. Okay, I won't torture you with 5 minutes of other material, so I think we'll stop here.
Well, thanks to Max for agreeing to this
No problem.
guest lecture.